session. We are looking into space, towards a galaxy, a giant galaxy, 500 billion light years away from us. Sorry, 500 billion kilometers away from us. Very big galaxy which was suspected to host a supermassive black hole in the very center. 101 years ago, someone discovered a streak of light, which is plasma shooting out of the center of the Milky Way, marking the supermassive black hole. I never believed that this black hole was as big as people said, until we saw that. This is the nucleus of the galaxy M87, and this is the first ever image of a black hole. Das ist das erste Bild eines schwarzen Lochs.
This is the first image of a black hole.
C'est la première image d'un trou noir. What you are seeing here is the result of many people working together. You have probably seen many images of black holes before, but they were all simulations or animations. And this is so precious to all of us, because this one is finally real. What you're looking at actually looks like a ring of fire. And it's actually created by the force of gravity, by the deformation of space-time, where light actually goes around a black hole, almost in a circle. And that creates that circle that we see here. It has a diameter of, I forgot the number actually. 100 billion kilometers. Now I got it right. It has 100 billion kilometers. But actually, at the distance, at the huge distance of M87, it actually will appear as a mustard seed in Washington, D.C., as seen here from Brussels. The size of the ring is actually determined by the mass of the black hole, and very independent of all the parameters of the black hole or the modeling. And so we can derive from that size directly what the mass is. And it's 6.5 billion times the mass of the sun. That is an enormous black hole that we see there. We see also more in there. We see this dark region in the middle. I've always been asked by my colleagues, or told by my colleagues, you cannot see a black hole, can you? And I think they're right. You cannot see a black hole, but you can actually see its shadow. And that's when the light actually disappears behind the event horizon, creating that dark region, that dark shadow we see there. And this is amazing if you think about it, where if you know the story behind that image, we're looking at a region that we've never looked at before, a region we cannot really imagine being there. It feels like really looking at the gates of hell, at the end of space and time. The event horizon, the point of no return. That is awe-inspiring to me at least, but it's also important for physics. I think my colleague Luciano Rezzolla will now continue and explain to us why this is so important.
Questa è la prima immagine di un buco nero. So black holes are part of our daily knowledge. In fact, even a child knows what a black hole is. And the best definition I've received actually comes from a child who simply said, well, it's just a hole you cannot fill. So they're very simple, but they're actually extremely problematic in physics, and because of the properties they have. The first property is that at their center, in a single point, we think the laws of physics break down. We call this point a singularity. Another property is that this singularity is covered by a surface, a mathematical surface, which is called the event horizon. Gravity is so strong on this surface that nothing, not even light, can leave it. And this surface separates the interior from the exterior, and nothing from the interior can leave and be transmitted to the exterior. And for a scientist, this is a drama, because scientists want to know everything about every corner of the universe. So having a region where you say you cannot experiment there, or you can experiment there, but you cannot tell the results of the experiment, is extremely frustrating and puzzling. And the same puzzling thought was shared by Einstein. So how do you get to terms, you come to terms with this idea? Well, the first thing you want to do is convince yourself that black holes exist, and in particular an event horizon exists. And the image we have produced does exactly that. So you may wonder, how do you know it is a black hole? And that is because it matches extremely well with the prediction that we can do from theory. And this is shown in this picture over here. So on the left, there is the observed image. On the right, there is a theoretical prediction. And as you can see, the analogy is remarkable. As a matter of fact, we have carried out over these last 6 months the most extensive investigation of what happens to plasma, to matter, as it falls onto a black hole. We have used supercomputers and highly advanced numerical codes to calculate what happens. And what we've learned is that as matter falls onto the black hole, it will start rotating at speeds which are close to the speed of light, and will become hot and emit light, especially in the radio frequencies, which are the ones that our telescopes can capture. But these simulations are not sufficient. If you want to know what a black hole looks like as an image, you need to take into account that light doesn't move on straight line near a black hole. Just contrary to this room, light can come from all sorts of places. And so light can be bent, can be lensed. And so the image that you obtain by looking at a black hole can be very counterintuitive. And we have carried out a very extensive investigation. We built tens of thousands of synthetic images which cover all the possibilities that we think are realistic conditions under which a black hole is formed. And this is how we have come to conclude that this is a black hole as predicted by Einstein. Now, you may ask, what is the meaning of this discovery? For many of us, it has different meanings, but there is one meaning that we all share and is very precious to us. We have transformed a mathematical concept, that of the event horizon, something that I normally write on a blackboard when I lecture on this, into a physical object, something that we can test and we can measure and we can observe repeatedly. And you may think this is a minor thing. Actually, this is a fundamental first step in any scientific progress. It's a scientific method. Be able to make an experiment and deduce from this what are the, how does nature work? And now I'll leave the word to my colleague Eduardo Ros to explain how this beautiful experiment was first carried out.
So, astronomy is not something that you do just from your desk. In many cases, you have to embark in an expedition. And 2 years ago, a large team of astronomers embarked in expeditions to the most remote places on Earth, in places where the atmosphere is thin and dry, because we need to observe at a wavelength where the atmosphere is important. The important thing of that is, in these locations are also facilities, as you see. They are like Iran 30-meter telescope or ALMA or APEX with European technology. And in these telescopes, the team of astronomers went there prepared with one eye into the weather forecast, checking up all the systems of the telescopes, checking that everything works, and waiting for the go command when the weather was good in all the sites around the Earth. One of the tricks you need to make such an image of a black hole is to get a telescope as big as the Earth. And to get that, the small pieces of this telescope are parabolic antennas, which you can see the locations in the picture there. These teams were observing that. We had a fantastic good luck because we get good weather all across the globe at the locations of the telescopes. These data were stored in disks because you don't have optical fibers there. You have to fill boxes of hard disks, pack them into an airplane, in some cases waiting for several months, like in the South Pole, until the winter over is gone, because it was night in April 2017. You wait them, and these data are sent to processing centers where they are played back as they were recorded and synchronized with atomic clocks. These places are like in the Haystack Observatory in Massachusetts in the US, or in Bonn, Max Planck Institute. They are the so-called correlators. Data are played back, they are evaluated, and then they are given to a further team who checks this data. Every telescope is different. You need to correct for the characteristics of each telescope, put all that together so that you get a telescope as large as the Earth. And this process needed also several months of hard work, assessment, iterations, until people were sure, okay, this is the data that now we can begin to image. We can extract the information from this precious data, which